trying to extend what happens in whole world from your little flat Earth neighborhood is almost impossible, because all the information you have is falling up at exponential rate. So if your error was 10 to the minus 16, by the time you're in Macon, it's of order 1, so it's useless. However, if the game is that every neighborhood you're supposed to little map, Atlanta, Georgia, Alabama, Colorado, all the way to Alaska, you have a local map which is flat Earth, but you demand that they overlap with minimal error and they fit on the globe continent, then you'll have very high accuracy thing. So sometimes, and in cases where things are very unstable or unpredictable in any particular trajectory, the global methods are much more powerful than local methods. This is mostly a minority view because all my colleagues have invested their professional lifetimes into integrating forward in time, because they are in people who haven't moved beyond Newton. Newton says step, 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 solve step, step, steps. And this is not the way to solve problem of turbulence. And I'm quite confident that I'm right, but nobody wants to throw an integrator they develop from their graduate school to their full professorship and say, well, that's stupid, I need a different method. But I believe that that's true. I'm a barbarian, so this book is book on ordinary differential equations, few of them. That's what this book really is. I mean, it has some other name, but that's what it is. Now, book on partial differential equations, I've never, they must exist, but I've never used one. So what can I say? A barbarian. There might be a beautiful, they all look totally old-fashioned to me because they all move forward in time. And I think as a field theorist, where I think in space-time. Now that book is chaos, but it's not written anyplace else that I'm aware of. But if you straighten me out, I'll definitely cite it and study it myself. And I understand it's a cultural problem. It's very hard to learn physics or mathematics or applied mathematics. It's really hard. We're just humans and we can learn a few things. So applied mathematicians learn how to do very difficult numerical calculations in the settings in which it seems correct to separate space and time. So there's no reason in the world that they would think of quantum mechanics or special relativity, because the thing is, oil is moving down the pipe and it's 6 meters per second. So time is time and space is space. What's the problem? Quantum field theorists know that they have to use all the symmetries, they have to write the action, and they have to do something with it, but they don't know what to do with it because it's very complicated and nobody taught them how to solve difficult numerical problems. So that's not what they're going to do. They'll just cook up more symmetries and go home and be happy. So someplace somebody has to do real work, and you have to combine the ideas of space-time, and you have to combine the ideas of fourth order, somebody's integrator, but it has to be optimization problem, so it's somebody else's problem, and etc. So this all will happen, and people will do it, and people are doing it, but it takes time. What Strogas teaches you works perfectly for problems in his thesis, and that's all he needs to teach you because he doesn't have to learn much else. Now, what I have to do, I have to learn some new stuff. I can, this is not in my thesis. The things that seem to work fairly well are papers that have someplace Kuramoto Shivashinsky or Berger's equation someplace in abstract or title. There's sufficient literature on them. Physically they're dubious because only Navier-Stokes is the real thing and Euler is the real thing in 2 or 3 dimensions. But in terms of what you can explore in one dimension, they're very helpful. And for those, they're nice integrators. So you will learn very quickly, everybody will cite a very nice integrator, very clever one for Kuramoto Shibashinsky, developed by Nick Trefetten. So that happens to be the path we have chosen. Now, nobody says that there aren't infinitely smarter paths than what Predrag and collaborators chosen. So if you find a much smarter thing, I'll follow you. I mean, I'm totally, I have nothing invested. If all of this dies, I'll still get my monthly salary, so I have no problem. This, and I'm not begging anybody for money right now, so I don't have to pretend that this is important. Okay. But, that's my recommendation. So there is a large number of machine learning papers, all of them testing their ideas on our papers, regardless whether they cite them or not. You can see that they use the same units on the axis, even though they don't cite us. That doesn't matter. But, it's a standard machine learning testing ground. How do we solve PDE by not letting machine figure it out? Okay. Machine learning of some kind.
Thank you.
Yeah, sure. Bye.